Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Good morning, Mike.
Hey there.
A little bit of moody weather for us today, a little bit of rain, but it's peaceful, pleasant. Birds are singing their songs outside over here. I'm enjoying it. How you doing?
Doing pretty good. I got sprinkled on this morning when I was running, which was actually kind of cool.
Oh, that is pretty cool. It's nice going in the ocean with a light rain like that, a little patter of rain. At the pool that I go to, the coach sent out an email saying, if you're coming to swim this Saturday and there is thunder and lightning, we will make you get out of the pool. And tell me if this part's surprising to you, you can't go anywhere that's wet, including into the showers in the gym. You have to be on dry land, no showers.
Mm,
Have you heard that before? Can't take a shower when there's lightning?
I have not heard that before. Like the showers are not outdoors though, right?
No, they're indoors. I mean, it's in a gym. I've
Mm.
heard this before, and I didn't know if this is like a folk wisdom or a real thing that you can get somebody who knows electrical can tell us. Can you get electrocuted in the shower when there's a thunderstorm outside?
It's a good question. I'm a little nervous about taking showers now.
For someone who knows the answer, it's probably just screamingly obvious. How could you guys not know this? But I didn't know that. I don't know. I've heard it twice now in my life, and each time I'm like, is that true?
I grew up in thunderstorm country and we had like lightning rods in our house, so I just
Oh,
assumed we were safe.
oh, okay. We don't have those. So maybe that's our problem. If you don't have a lightning rod, maybe you're not safe. Mike, what have you been listening to over the last couple weeks?
So there's a couple of metal bands that have been around for a long time that recently came out with new albums. One is by the band Neurosis. I don't know if you ever
Hmm.
listen to them, but they put out their first album in like a decade. It's called
Hmm.
An Undying Love for a Burning World, and people seem to love it. It's got lots of good reviews.
They're
Um,
ones with classical, inscrutable metal font that you can't read, right?
One of them,
Like,
yeah.
yeah.
um, the other the other one is by the band Lamb of God.
Mm.
Another
You've
band
mentioned
that's
that before to me.
yeah, they've been around for I don't know 20 years, I guess. And they have a recent album out from I think February called Into Oblivion that I've been listening to a lot. It's very aggro, not like super innovative, but kind of what I needed at this point in time for some reason. There's some pretty pointed lyrics, kind of metal lyrics, not like great poetry, but there's this one song that I really like called "The Killing Floor,"
Hmm.
and it has this the chorus is bow down to the butcher slaughtering your future on the killing floor.
Phew.
So I thought that was you know kind of delightful,
Oh, delightful. That's
charming.
actually pretty similar to the type of stuff I've been listening to all week. I fell into a hole and I've been listening to Bill Evans' Conversations with Myself for the
Also
last couple
very
weeks.
also very metal.
Pretty metal record. I didn't know this. I looked it up. It came out in 1963. I know you've heard this one, right? I'm pretty sure I've foisted this on you at some point, right?
Yeah, I think I've listened to everything Bill Evans that can be listened to without like going into a record store and buying it.
Mm-hmm. So the thing about this record is I've been listening to it for 30 years. It's quiet jazz piano. Bill Evans, for people who don't know, played with Miles Davis on most of the tracks on Kind of Blue, not all of them. He was a classically trained pianist, and he made this beautiful sounding music. And I just keep coming back to it every so often. This record in particular, he did this thing where I guess it sounds really ambitious to me. He would record one track and then he would play it back and he would record another track where he was accompanying himself. And he actually did this on 3 separate piano tracks for most of the songs. There's a couple songs there are only 2, but it was like he made up his own trio by listening to himself and then playing back along with himself. So there's no other instruments or musicians on the record. And I always think, oh, that sounds probably pretty hard. But the result is this intricate and layered music. And it's just like unlike anything I've ever heard anywhere else. It just feels like there's these like special puzzles in my brain, these boxes where like the keys to open them are the tinkly piano sounds that are interwoven and interleaved on this record. It just like it does something in my brain. I don't get it. Sometimes I need this like quiet, contemplative, just alertness. And this is like easily one of the greatest things I've ever heard. One of the greatest pieces of music ever recorded. I read later that when he, at the time that it was controversial to do overdubbing on jazz records, because people were like, well, you shouldn't record something you can't go to a club and just play. And so obviously Bill Evans can't play three versions of himself at the same time. And so he wrote, I remember reading the liner notes for this record when I first started listening to it. I mean, I had it on CD, but he wrote this. I returned to this the other day because I was like, what is the story of this thing? And how did this come about? And the description that is in the liner notes that he produces is like philosophically rich description. I want to read it to you. It's kind of weird. So he says, and he's kind of trying to address this controversy of, yeah, I couldn't go to a club and perform this album. To the person who uses music as a medium for the expression of ideas, feelings, images, or what have you, anything which facilitates this expression properly is his instrument. So, sidebar there, he's like, recording techniques and overdubbing is the instrument, which doesn't sound controversial to us. I mean, we listen to like electronic music, right? Like, yeah. So, but anyway, continuing on, he writes, I remember that in recording the selections, as I listened to the first track while playing the second, and the first two while playing the third, the process involved was an artificial duplication of simultaneous performance, in that each track represented a musical mind responding to another musical mind or minds. The argument that the same mind was involved in all three performances could be advanced, but I feel that this is not quite true. The functions of each track are different. And as one in speech feels a different state of mind making statements than in responding to statements or commenting on the exchange involved in the first two, so I feel that the music here has more the quality of a quote trio than a solo effort. There's so much in these words that sort of stimulate my brain. Where he's like, when you're listening to something and playing back, your mind is in like a different mode. You're communicating. You're responding. I just started thinking about, and this is probably a crazy leap, but like it doesn't make any sense to anybody else. I started thinking about like bootstrapping with data. I started thinking about like we've been using these models a lot, and there's this weird feedback loop that you can get into with them where you think I mean, I write code this way, but I think I've got the answer. I've got the idea. I spit out, I tell the model, I want to do this. Can you just do this? And I'll be like, yeah, that's mostly good, but what about this? And I'll be like, damn it. I had all the ideas. Okay, we'll use that too. Okay, fine. But I'm still the guy who had the ideas, right? There's like this feedback loop happening, and there's like an identity and an authorship problem that it always poses for me. Okay, if you would like to reach us, we can be emailed at podcast@picturemecoding.com. We are also on Blue Sky under Picture Me Coding, and we have a Patreon account. If you like what we're doing and you'd like to support our show, the Patreon membership level that we have is $4 a month. It's not very much, a cup of coffee, but the idea is that we would use those funds. We do not plan to have ads on our show, so we would use it for hosting costs and editing and things like that. But you're also welcome to listen and hang out with us even without being a Patreon member. We welcome all comers.
I read something recently that those things are called CTAs, or
What does
calls to
oh
action. And
yeah, we're calling to like to go join our Patreon as a call to
yeah,
action.
and this article that I was reading said that you should probably only do one of them at a time, because
Oh,
if you
don't email us and also talk to us and
yeah,
also call to action on our join our Patreon.
yeah. So,
Like
but
and subscribe and smash the buttons, right? This is what they used to say on the
yes,
thing.
but
Okay.
since we have a higher quality of listener, they can probably handle more than one.
I have a lot of respect for our listeners. Maybe that is self-serving. I like the people who write to us. I like the people who say to me, "Wow, I listened to your show. It was really cool. I got," and they just start talking about stuff. And it's like, yeah, you get it. Yeah, yeah. I was interested in that too. Let's keep going. you know, let's keep the conversation going. Yeah, I like the. I like the kind of small community that we have out here. So if you're listening to us, thank you for hanging out with us. We're glad to have you.
So yeah, the topic. I've been doing a lot of database stuff over the last year, and I guess I've been doing database stuff for decades now, particularly with SQL and relational databases. At some point, I think everybody who does database stuff, particularly with SQL, sometime during that journey, you discover query plans.
Explain.
You,
I can almost remember it. Yeah. Like, whoa, what did
yeah.
you just do? Explain? What the hell is that?
Yeah, so this is amazing thing that you discover at some point is if you put explain in front of your SQL query, it will spit out this thing saying, this is how I'm going about querying the database in this
Oh,
particular case.
I loved it when I found it. But then I was also like, do I really understand what I'm getting? Sequential scan sounds bad. Index scan sounds good. What else is all
Yeah,
this noise?
they can be extremely complicated to read, and they're different from one database to another, like the form of them. And I discovered in either 2024 or 2025 that LLMs are kind of like query plans are kind of like the killer app for LLMs. You can say, "Hey, explain this to me," and it, you
Oh,
know, goes through all that and gives you a better breakdown. But in the process of doing this over the last year or so, it kind of occurred to me, I don't know where this idea originated.
yeah.
It's an interesting aspect of computer science to me, and I don't know where it really came from. So the idea that we're talking about is query optimization or query planning, I guess. So I decided to, do the thing that we do and go out and start researching where this
Hmm.
idea originated.
It sounds very hard. Like if somebody came to me at work and said, "Hey, I want you to optimize the way our database queries are happening. I want you to pre-analyze what the query is going to like the effort maybe is going to go
Yeah.
through to produce the answer and then make it more efficient." I'd be like, can we get somebody else to do that?
So the rough idea is that when you do a SQL query, it's sort of a declarative language. It's
Mhm.
not telling the computer how to do it. It's telling it what what you want at the end. And
Yeah, from COD, right? Sequent calculus, right? Like set theory. It's set theory ultimately.
it's set theory, and so there can be different ways to actually execute the query depending on certain factors, and particularly when you get into multiple joins. And I started looking into this, and surprise, it originated with System R.
Oh, yeah. And
So
we read? It was Jim Gray. Was it Jim Gray when we did his
yeah,
work? We learned about System R and COD and
so we did an episode on Jim Gray, and we talked a lot about System R, and we did an episode on relational databases too. And so this is going to turn out to be sort of a combination of two series that we've done in the past. So we did this series that we call Shoulders of Giants, where we talk about significant computer scientists from the past, and
mm-hmm, mm-hmm.
um, we
So this is like
also
a Pizza Hut Taco Bell combination of
exactly, and we've done a series on databases, and so this is kind of like a combination of
church.
Shoulders of Giants and databases.
Okay,
So
cool. I'm
the
with you.
sort of key paper about this topic was written by primarily by a computer scientist at IBM named Patricia Selinger.
Like a lot of these papers, it has a funny what's the type access path selection in a relational database management system. I can't imagine being a librarian. It's like I want to know how this. You come up with the name of this paper and your access path selection. Be like what?
Yeah, it'll make a little bit more sense when we get into it, but
But
um,
but but this paper you sent to me, I tried to read it, I got a little stuck, but the thing I like about a paper like this is it's like it's foundational and it's extremely central to all the work that happened afterwards. So it's like this incredible access point to see the tree root of a lot of these ideas.
yeah, it turned out to be very significant, and also is still the basis of a lot of what is happening in relational databases.
Hmm.
to this day in 2026. And a little bit about Patricia Selinger first, maybe. She got all three of her degrees, her bachelor's, master's, and PhD from Harvard.
Hmm.
Her PhD was in applied mathematics. Right after she got her PhD, she joined IBM Research in San Jose, which I think is also where Jim Gray was,
Mm.
and started working on the System R team. There was kind of a problem with relational databases at the time. There was this notion that they really couldn't ever be made efficient enough,
Mm-hmm.
especially when you were joining across a large number of tables. People had developed sort of heuristics to try to speed them up, but nobody had really solved the problem entirely. What she started working on, went into the System R group at IBM, and a few years after she had started there, she wrote this paper on the work that she'd been doing, and the idea that she came up with is now what's called cost-based optimization.
Hmm. And the
And
cost is like, it's like computational cost. Like, how expensive is it to query this in terms of how long it'll take, how many rows,
yeah, it's
how many disks seeks and stuff like that.
yeah, it's in terms of the amount of IO and the amount of computation combined. So,
Hmm.
it presumably would map to actual dollar cost, but they weren't trying to figure out how much it was going to literally cost them in money. They were just trying to figure out how much IO and computation was involved.
Hmm.
At this point in time, System R was reasonably well established. Michael Stonebreaker was working on Ingress, and so the relational database ideas were pretty well established. I think this paper came out in '79. Is that
Hmm.
what we?
I don't know
Uh,
actually.
the basic idea that she and her colleagues came up with was two key parts. Is that one is you have to make an estimate of how many rows are going to need to be read from the database, and how many, um, at the time they called it page fetches, would need to be executed to get that data.
Hmm.
And
And when you do like an explain it, usually will say like 0 to 4 million rows or something like that when it does a sequential scan. So it has an idea. Oh, I got to look at these 4 million records to issue this part of the query.
like if you do this in Postgres, it will give you these slightly cryptic numbers, but the basic idea is that there's a cost in terms of the number of rows that need to be returned to
Mm.
get the
Hmm.
data
Hmm.
for a particular query. They developed this system where you had to have some statistics in the database to begin with in terms of how big's the table. They talk about it in terms of cardinalities.
Oh, yeah. How many? The count.
Yeah, the count of rows in both the table and potentially in indexes. In the paper, they talk about something called RSI, which is like
Yeah, I saw that.
I think that's the underlying storage engine for the System R
Oh,
database.
so it's like the IO stuff. Like how much IO we're gonna run.
I think this was actually their measure more of CPU usage, because
Oh.
the cost function they started out with is fetches plus some arbitrary factor W times RSI calls. So what it says in the paper is RSI calls is the predicted number of tuples returned from the RSS, or the research storage system. Since most of System R's CPU time is spent in the RSS, the number of RSI calls is a good approximation for CPU utilization.
So roughly, we're computing CPU IO in order to figure out the cost, and the goal is to optimize that. There was a section early on in the paper that they talk about how she talks about how SQL sort of works, and I was like, oh, I get this. Before I got real lost later on, so I'm going to read you the section that I got. This is a preamble. How does it work internally? She writes that each SQL statement sent to the parser, where it's checked for correct syntax. A query block. I like this. I can understand this in my head. This part. A query box represented by a select list. Those are the columns we want to select, right? A from list. We've got two lists now, and a where tree containing respectively the list of items to be retrieved, tables, references, Boolean combination of simple predicates specified by the user. I kind of like this because it's like, oh yeah, that makes sense. So it's like an abstract syntax tree where the where could be yet another query, right? Where something selects from some other query, potentially sub-select or whatever. The 4 phases of statement processing are parsing, optimization, code generation, and execution. And this paper is really focused on the optimization and code generation part. So that middle part there, not parsing it. So that's where we get into how they're optimizing and generating the equivalent code for what's going to happen. Is that right? I think that's what's going on in this paper.
Just as a note, this is still pretty much how most database systems work. There's a parsing stage and then, an optimization planning stage. It kind of depends on the database, how that actually goes, how that actually happens.
Mm-hmm.
But
This is another cool thing when you read a paper like this from the 70s and it's like, hey, I came up with these ideas, we're using them, they work well, and oh, by the way, come to find out, people are still using those same ideas.
yeah, so you parse it, then you do this optimization planning phase, and then the third phase is the part that actually takes the plan and executes it against
Mhm.
the storage layer.
So they have this formula, which is their cost. I didn't quite follow the formula, but we'll just move on from it. Okay, we'll just wave our hands over it, right?
Yeah, just
So
think of it as being like the cost of IO plus the cost of computation, I
yeah,
guess.
and probably a super trivially obvious thing. You want the lowest cost plan. You really want to do the least amount of IO and CPU in order to get the answer for the user. But it could be hard if you've got a couple tables that have millions of rows in them. And there's some like filters, like where clauses and other stuff. Like, how do you actually do this?
So this is where the access path part of the title of the paper comes in. It turns out that there are often multiple different ways that you can try to go out and get the data. Even for the single table case where there are no joins, there can be multiple access paths to get the data.
That statement kind of surprises me. So if I just do like select star from some table, you're saying there's multiple ways I could get that.
So if you're doing select star from a table, there's really only one way. You kind of
Oh,
have to do the sequential scan, or what they call a segment scan in the paper, because of the fact that there are no predicates. There's no
mm,
where clause on that.
mm-hmm.
But
You
when
pretty much
you
saying I want everything. Give me everything.
yeah, you're saying you want the whole table.
Okay, so that
But
instinct isn't too wrong.
but if you start adding where clauses or other parts of the query, then
Hmm.
even with a single table, you can have multiple access paths.
So
So
so get me all podcasts where the hosts are rad and over 40 years old.
potentially, yes. When you're looking at the podcast host table there, you've got two conditions, and so you might have index on one or both of those things.
Now indexing
And
changes the story significantly, right? Because you want to try to use the index if you can. Should we talk about indexes?
well, let's talk about it a little bit in the sense of, an index is also a thing. At the time they were working on System R, I think these were B tree indexes.
Oh,
But
at the time, B tree, the B plus thing. That paper had been around since the 60s, right? Anyways, I think I'm getting us off topic here. So indexes.
so in any case, the index is it's still a thing it's stored on the disk. So it's something that you still have to go out and fetch from some storage device at some point in time.
But let's say
So
you've got millions of podcasts in the world and you've got a title for a podcast, and that's probably unique for every single podcast. And then you've got maybe the ages of the hosts. Like it could be, if you're going to query on those ages a lot, it could be valuable to query on the ages, because put an index on the ages, because maybe you shouldn't do that. Maybe that's ageist. What if some non-ageist feature? Topic. Let's do topic. Okay, so topic, right? So there's
I think
probably a much smaller subset of topics than podcasts. There's got to be. So you could store an index of those alongside on disk, right? That's what you're saying?
yeah, there's a kind of an important point here. So let's go with the age index, even if it
Even if
is
it's shitty.
ageist. I mean, we're old, so we're allowed to be ageist, I think,
To ourselves.
to
Okay.
ourselves.
All right. Okay.
So let's say there's an age index. There's an age field, which is, say, an integer,
Integer.
and
Yeah.
and we put an index on that. So for selecting from the podcast host table, and we're putting a where clause in there to filter by age, it
Mhm.
might make sense to have an index on the age. And
And the index, again, is gonna be a lot smaller than all of the age it's not gonna collect all the ages, it's just as, like, it's a key into them, like, here are the rows where the ages are between these values, right?
so you can sort of abstractly think of it as, here's the rows where the age is 40, and here's the
Yeah.
rows where the age is 41 or something like that.
Right. Right,
Um,
right, right.
Theoretically, the index is smaller than the actual table.
Mhm.
Also, another interesting thing about the index is that they are usually sorted on disk, and that will come up later. But so let's say that you try to select from that table and you use the age as one of the criteria. It's likely that you have two options now. You have the full table scan and you have the index scan.
Mhm.
And in this case, the with query planner is probably going to choose the index scan because it has to do less IO. Now, you mentioned also potentially having a topic. Now, the problem with
Uh,
topics is that they are not necessarily discrete values. So the topic might be just an arbitrary string.
oh,
Let's
okay.
let's say in the
Okay.
database that it's a
Like a
varchar.
music podcast about software, there's only one of those in the whole database in the world.
Yeah, so if it's not some well-defined discrete set of values, then you might end up doing a query like a like query,
Mm.
um, or like a prefix query or something like that.
Mhm.
And so what they talk about in this paper is there are two types of criteria. There's SARGs and non-SARGs, or sometimes people say sargable. So um,
Sargable. Which one of my queries is sargable, Mike? I think I
so
want that, right?
yeah, so the age index is going to be sargable.
Okay,
Um,
because I got this cool index and it's like a good way of doing less IO.
yeah, at this time, if you wanted to do a topic lookup, but you didn't know, you were just looking for like keywords or something, and you wanted to do a like query, that would probably not be sargable because at every evaluation you have to do a sort of computation
At every row,
at
ultimately
every
what you're saying, right? Like
yeah
I go row by row. Does this column match the
yeah.
predicate?
And this was before the days like Postgres now has full text indexes, which would help, but they did not have that at this point in time.
Hmm.
So in any case, and like if you had two or three sargable predicates on the where clause, you could potentially have indexes on all of those.
Hmm.
And so you now have even for the single table case, you have multiple possibilities to look at,
Okay.
which is going to be the better index to use.
Hmm.
Also, there's this thing they talk about in the paper called selectivity factors,
Hmm.
and apparently this is still a thing that's again part of modern optimizers.
Hmm.
But the idea is that for certain criteria, there's this estimate of how many rows you're likely to return. So if you do an equals, like an A equals 10, um,
Hmm.
then that has if there's an index on that, then the selectivity factor is basically going to be an estimate of, I think what they use in the paper is 1 over the size of the index.
Hmm. Hmm.
So the idea is that
One element of the index out of all of the possible elements in the index.
yeah. So the idea is it's supposed to give you an estimate of how many rows are likely to be returned by that
Oh.
particular criterion.
Okay. Okay.
And
Okay.
if it were like a greater than query or a less than query or something like that, then the selectivity factor is going to be different and will probably you'd expect more rows to be returned. And so
Hmm.
if it's making a choice between two indexes and one of them is an equals and one of them is a greater than, then it's likely to choose. It's not. 100% certain, but it's likely to choose the equals case because it's going to return fewer
Oh.
rows.
Okay, I got lost on that in the paper. What you just said makes a ton of sense because my naive thinking was like, well, don't you just pick whichever index is smaller? Like that's a smaller set of things. If it's this and this, right? I start with the smallest possible subset and then I go from there. But no,
Yeah,
you're saying that the equals the greater, like the way in which a where clause is defined. Intuitively, this makes a ton of sense now that you explained it. It was not obvious until you made it obvious.
there's another thing that they talk about in here, which also comes up even on the single table case, which is something they call in the paper interesting orders.
Yeah, I didn't. I like the phrase, but I didn't understand it. What does that mean? Is that when you have an order by?
It comes up in the single table case. It comes up when you have an order by or a group by, and apparently this term has persisted into modern optimizers. It's still,
Interesting orders.
yeah, it's still a thing
Like you
that
go to the
comes
coffee
up.
shop and they go, "That's an interesting order," but the
So
coffee shop here is the table optimizer.
the reason why it's an interesting order is because I think I mentioned this earlier. Indexes are already sorted.
So if the index is already sorted and the user is requesting a sort order that matches an index, you could just go straight to the index. Is that where we're going with this, or that's too dumb?
That's pretty much it. Yeah. So the reason this comes up in the optimizer and the query plan is that now you have two options. One possibility is, well, maybe even three options. So there may be an option where it makes the most sense to do a full table scan. There may be an option where it makes the most sense to do the retrieval using an index and then subsequently do a sort.
Hmm.
Or there might be a case where it makes the most sense to use the so-called interesting order index to find the data in the table because then you eliminate the sort.
Hmm.
You end up with a situation where you can retrieve the table in a sorted order and then you apply the predicate in memory to filter out the rows that the rest of the where clause has, and
Jeez.
that may turn out to be the lower cost option in some cases, which is why order buys and also group buys are considered to be interesting orders.
Huh. So one thing I naively used to see is I would say, oh, it would say, I'm just going to do a full table scan. This table's really small. And I'd be like, well, you've got an index. Why don't you use the index? And I used to forget, well, the index doesn't have all of the, I mean, they're tuples, but they're actually like every single column. Like the index doesn't have that. So like you asked me for answers. I still have to go and look up those answers. Okay. And I could go to the index first and then go to the answers. But in your case, your table's so small, I'm just going to go to the answers. You don't have big data, is what PostgreSQL tells me all the time. You don't have big data, my friend.
Yeah, especially
We
in
haven't even
the
talked about joins yet. Go ahead. Go ahead.
especially in modern times. If you have a small table, it may already be in memory. Another thing, they don't really talk about this in the paper, but I encountered this early in my career, is that sometimes you'll make an index on a column where it only has a few actual values,
Mhm.
and
So the index is not that informative in that case?
yeah, so you end up with some cases where the index is very big, and y- so loading the index and then using the index to scan over what turns out to be a big chunk of the table anyway turns out to be less efficient than just doing a
Oh.
full table scan.
The more we talk about this, the harder I think it is. But you are helping me understand the paper. I really did not understand it, but I was so lost. Some of the language in here is so dense. You get to the joins, and I was like, okay. I tried like 4 or 5 times to read this, and every time I got to the joins, I was like, can I just have Mike explain this to me?
Yeah, so let's talk about joins a little bit. Joins make things much harder. And
Yeah. 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 Do you want to tell me why? Do you want to describe why?
so you still have all the issues that we talked about in the single table case. You have indexes to deal with and you have orders to deal with and so forth.
Hmm. So the fundamental problem is there are lots of different ways to select the data. There are lots of different ways to say, I'll look at that, I'll look at that, I'll look at that. I've got these indexes, I could look at those. the optimizer has to pick a strategy that's going to be reasonably efficient.
It can make a huge difference in some cases too. Doing the optimized version over the naive version can
Hmm.
sometimes be orders of magnitude faster.
Yeah,
But
I mean,
when
I've had problems at work where it's like I added an index and suddenly we were going from minutes to milliseconds to do things.
So if you think about joins, what happens with joins is you've got two tables that you're trying to connect through some key.
Hmm.
And you usually write the query in such a way that you sort of mentally think of one query as being the left, one table as being the left table, and another table as being the right table. Or if you've got a chain of them, you sort of think of them as being in a particular sequence. But
Yeah.
from the standpoint of the actual database, the order in which it does those joins may have a huge impact on the efficiency of the query. You
This is
know,
the part I'm really naive to. Every time I write a query with a lot of joins, 5, 6, 7, 8 more, I'm always like, oh man, I'm probably writing this very stupidly. And then I try to like in my head, like, let me start with the smallest tail. I know which one's going to be the smallest. Let me start with that. Honestly, Mike, I have no idea if that's the right strategy or not. I just always kind of thought you want to start with the smallest set of rows and then I don't even know though.
so let's just like run through a really brute force case. Say you've
Hmm.
got two tables, A and
Hmm.
B, and you want to
Can there be
join them.
podcasts and what and I don't know.
Uh,
Email
pod,
addresses.
podcast table and podcast host table, I guess, or
Got it.
something like
Okay,
that.
right. Hosts are right. They're employed by the podcast.
So in the brute force case, what you would do is you take the podcast table, you'd look up a row, and
Hmm.
you'd say, okay, the value for this field in this row is 10. So I'm going to go over to this other table, and
And
I'm going
see
to
all
try to find all the rows that
all
have
the
the
matches.
10 for this
Yeah.
value.
Got it. Yeah.
And this is kind of what they call a nested loop join.
So it's quadratic.
Yeah, yeah, effectively. But it's the reason why you need the planner is because you don't know initially what the size of the two tables is. So really, it's like if one table is size n and the other table is size m, it's n times n
Hmm.
times m. If you've got like a million rows in table A, but you've only got 100 rows in table B, it doesn't make a lot of sense to go through all million rows in table A and then cycle through the 100 rows in table B.
Hmm.
So what the planner would probably do is instead go through the rows in table B and then go back to table A and look them up there.
Yeah, that
Um,
makes sense. But this is that an inner join? I mean, we're not talking left join, right join. We're not talking outer joins.
well, let's think of it as an inner join for
Yeah,
now.
okay, that helps
Um,
me.
the,
Right.
the
Inner join is the shared, right? In the Venn
yeah
diagram, it's the slice in the middle.
yeah the term left join is a little bit tricky right now, but we'll get to that.
An outer
Um,
join. Jeez. Got it. Okay.
So, like if the million row table has an index on it, it would make sense for to start with the smaller table and then use the index on the bigger table, for
Okay.
example. Basically, the idea being that you can do these joins in any order
Hmm.
and you end up with the
Is
same result. But
is that is that true? It's true.
yeah, you can do them in literally any of the orders. So if you've got n tables, you can
Uh-huh.
do the join in such a way that any of the n
Okay.
factorial permutations will give you the same result.
Okay, got it. Yeah, it's a set theory thing again. Yeah, like if you're always selecting this, it doesn't matter.
So again, if you've got n tables that you're joining, then there are n factorial possible permutations. If you think about that, so for 5 tables, that's 120. For 10 tables, it's something like 4 million.
Mm,
Checking 4 million potential join orders is not really a reasonable thing to do.
mm-hmm.
Um,
You don't want your optimizer to be running forever.
Interestingly, doing it the hard way, the n factorial way, is an NP hard problem. So
Oh,
if anybody's
okay.
ever asking you for an example of an NP hard problem, figuring out the optimal join order in the most rigorous way as an NP hard problem.
Okay, all right. So it's not solvable then, in a way. Like there's no efficient way to solve it. So we have to do something. And that's what the paper is about. Like we're just going to go this way.
The paper develops a technique that gives you a pretty good result without doing the full n factorial problem.
Hmm.
And it's kind of it's a type of dynamic programming that they come up with. So
Hmm.
I don't know how much we need to define that term.
Don't want to.
Okay. Um, Roughly speaking, the idea is, you start out with small pieces and work your way up to bigger pieces. And
Hmm.
so effectively what they do here is they start off with the individual tables. So, say you're joining three tables, you look at all the possible strategies that you could use to query those three tables individually.
Hmm.
There are some restrictions, or there's what they call a heuristic, where they eliminate certain possibilities right off the
Okay.
bat.
That's what I was asking. Because I was going to ask, because you said if you had 10 tables, you're talking 10 factorial, you're looking at 4 million. You can't look at all of them, obviously. There's got to be some pruning that happens. And the pruning has to be sort of guessy, right?
Well, there's one type of pruning. There's one heuristic they use, which is sort of an absolute thing. So the rule that they use is, say you're joining three tables. I'm just going to call them A, B, and C for now. But
Hmm.
say you're joining A, B, and C, but you're only joining A to B and then B to C.
Okay.
So there's no direct criteria between A and
A
C,
and
which
C.
join
Got
them.
it. Okay. All
So
right. All right.
um, this type of connection, which they call a cross product, they just eliminate those entirely from the set of things that they look at when they're doing the joins. So if there's no predicate that joins A and C, they don't even look at combinations of A and C, if that makes any sense.
I think it does. But it also, again, you stated a thing where now that you said it, I was like, well, that sounds obvious.
They look at the initial tables and they say, what's the best way to get these table what's the best way to get the data from these tables
Hmm.
individually.
Hmm. Hmm.
And so the example they give in the paper is an employee, department, and job tables that they're joining
Oh,
against.
the classic SQL
Yeah.
test example. We got your department.
Yeah. Um,
We got your
so
manager. Oh, they don't have that. Sorry, go ahead. But
so
yeah,
they
so
look
it
at
was select name, title, salary, department name from employee, department, and job. I never write table, comma, table, comma, table, by the way, but where title equals clerk and location equals Denver. And then they have these two joins where employee department number is the department number, and employee job is the job.
yeah. This was also before they had the SQL on. So the join statement with on, I believe. The join criteria just look like parts of the where clause.
Okay, got it. Okay, I did kind of translate it as an inner join in my head, but I was like, "Can you write this? Is this valid?"
Yeah. They look at ways to get data from the employee table, the department table, and the job table individually.
Hmm.
And they may eliminate some of the paths at this point. Like it may turn out that doing a full scan on one of these tables is clearly not the best option. So they don't have to include that in the paths going forward.
Maybe employees table is absolutely massive, but departments is small. Maybe job titles that's small, and they're not also what you said is they're not joining in this query employee to job. They're joining employee department and employee to. Oh wait, they're not joining department to job. They don't care about that, and so you don't have to actually look at those cross products.
Yeah. So once they've figured out a cost for the individual tables, they start looking at pairs.
Hmm.
The first level of join. So potentially joining employee to department, potentially joining employee to job, but and then also potentially the reverse of those. So
Mm.
joining
Oh.
department to employee,
Hmm.
joining job to employee. Um,
Because it's equivalent, and those might be a lot smaller. Yeah, it might be cheaper to
yeah,
do that.
yeah.
Yeah,
So
okay,
those
that makes
that
sense.
that that ordering may may turn out to be the more efficient. In the paper, they're joining employee to department, and they're uh, joining employee to job, but they don't join department to job.
Mhm.
So they don't consider that pair at all because that would be a cross product, as they say in the paper. So anyway, they now at the second level have all the potential pairs that they could do they could use for the first possible join out of
Mm.
joining these three tables.
Mhm.
As they're doing this, they're sort of building out a tree.
Yeah.
So
Yeah.
each of these potential join orders at the second level is like a branch on the tree.
Mhm. But here's where question comes in, because it's like you sort of have to pick a strategy. It's like a decision tree in a way. We're going to go this way. You pick a strategy, but the thing I didn't get from the paper, the thing I always kind of wondered is maybe the where clause has other nested trees inside, and do you have to evaluate all the way down to figure out your cost? Like, does the question make sense?
Yeah, it does. They actually have a section at the end of the paper where they talk about nested queries.
Hmm.
So the case I think you're talking about is where you can have like a subquery at some point in your query that generates its own set of data.
Hmm.
They do talk about that in the paper. I don't know how much we'll get into it,
Oh, okay.
but
All right. I'm asking a weird question then. So, so we've got the join predicates. We've got like a decision tree kind of thing. We've got a strategy that we could say, well, this table's smaller, so we can actually reverse the join. We'll pull from this first, and then find the related ones in this other one.
yeah. So at this point, you've got all the possible combinations of tube tables, and I think in the paper they've got four of them: employee, department, employee, job, department employee, and job employee.
Hmm.
And then at that point, they start looking at ways to join the third table, which is, it depends on which what their starting point is. So if the starting point is employee department, then they have to join to the job table. If the starting point is employee job, then they have to join to the department table.
Hmm.
One of the things here is that as they're going, they're sort of accumulating the joins. So when they're joining things, you're always thinking of it in terms of joining a left side to a right side in this
Yeah. Okay.
in this
Yeah.
in this particular strategy.
Hmm.
And as you go down the tree, the left side is actually like a combined. It may be the results of the join
Right.
rather
Like
than
there's
an
like an
individual table.
evaluation order, right? You
Yeah,
evaluate A join B, and then you evaluate that join C.
right. So when you get down to the third level, the left hand side is the various options of employee department, let's say, and then what are the strategies you can use to join that to job.
Hmm.
Or the left side might be employee job, and you look at the best strategies to join that to department.
Hmm.
This strategy over time became what people started to call left deep.
Hmm.
I
That was
guess
a hip hop group from the '90s, I think.
it would have been a good one. I guess they did it this way at the time because it was the most memory efficient. So they didn't have to store as much as they didn't have to store intermediate results in memory as they went.
Okay. All right.
Um,
But you're still, isn't there, so you're building a hazy picture for me. I think I'm getting it. I think I am. But aren't you evaluating along the way, and as you evaluate, you're sort of throwing away strategies? Is that happening?
there are some they're pruning, yeah, because they're clearly higher cost options.
Clearly higher cost, but some that might be lower cost. Is that instinct wrong?
So there's going to be you can't really determine the lowest cost case until you get to the leaves of the tree, basically.
That's the question I'm asking. Yes,
Yeah.
that's what I was trying to figure out. Yeah.
So they're not going to make a decision about the optimal plan until they get to the leaf part of the tree, but there are apparently ways that they can sort of prune the tree as they go because they know that using an index on this particular join is always going to be more efficient than doing a full
Okay, so
scan.
you pruning the trees you go, but it's still like it feels like you could get some really pathological tables where you get close to your 10 factorial, possibilities.
Yeah, I think they say in the paper that the maximum size of the table, assuming you don't eliminate any possibilities and you're doing joins between all the tables, is I think 2 to the n.
Hmm.
So
Say
it's
maximum size of the tree. Is that what you said?
yeah,
Maximum size of the table tree.
maximum size of the tree is 2 to the n.
Tree. Yeah. Right. Right. The
Um,
evaluation tree is really what we're doing here. Yeah.
yeah, so it can get reasonably large, but obviously is much smaller than n factorial.
Yeah. Okay. All right. All right.
Um,
Okay. So there's a limit on it. So it's not. It's just my gut response is, well, doesn't that ultimately get as big as all considering everything? If you don't have a good way of eliminating.
Selinger talks about them doing joins of up to 12 tables. Don't remember the number they give, but they said they can do 12 tables efficiently. It's, I think, on the order of seconds or something like that.
I
Um,
hate reading those queries.
yeah, that would be a gnarly query. Uh, yeah, so they build this tree, and then the access, the various paths through the tree are the access paths that they talk about,
Hmm.
and this dynamic programming approach will give them something which they hope to be optimal in terms of the cost. And again, this type of cost-based optimizer is still pretty much it's been refined a lot in the last 50 years, but it's still pretty much what happens. If you use Postgres, it has a cost-based optimizer.
Or
Although
MySQL.
I think MySQL uses this framework called Cascades, which, or no, I'm sorry, that's SQL Server. I don't know what MySQL uses, but
Mm-hmm.
in any case, there's some problems with this strategy that people have pointed out over the years, and people have made some attempts to improve on it. One problem that comes up a lot is what they call the independence assumption.
Mm-hmm.
So there's kind of this.
I think you sent me an interview with Patricia Selinger where she mentions this, I think.
She talks about a specific example, which is interesting because it's relevant to us. Imagine you have a table that has zip code and also state.
Mm-hmm.
You could conceivably have an index on both of those,
Mm-hmm.
and the optimizer could consider both of those as part of the access paths.
But they're
But
totally correlated.
yeah, but they're totally correlated because like as she puts it in this interview, the zip code 90210 is always in California. So
Oh, so the independence assumption says if the query planner just assumes that these indexes are independently valuable, but they may not be. They may be. It's kind of like in like a regression or something, right? Like where you find out these two variables are. Well, that's probably a bad example.
yeah, if you could pre-establish sort of that there's some dependence between them, then you could
Then there's no
sort of
point
you could
considering both.
eliminate certain access paths.
Yeah. Okay. 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 So
I
that's
think
the independence assumption. The assumption that all of these different indexes or selections are they're independently derived values. I guess that's the phrase I want. I'm not sure what phrase I want, but yeah.
I have read that there is a lot of databases now do take into account what they call order dependence. So if they know that two fields are ordered in exactly the same way and one of them has an index and the other one doesn't, they will use the index even though it's not technically the field that the person has a predicate on.
Mm-hmm. Well, because
Um,
it just happens to be ordered the same way, is what you're
yeah,
saying. Yeah.
exactly. Another issue that comes up with these is that they are very dependent on having correct cardinality estimates on the tables.
This
And
part, so you mentioned this to me, this surprised me. And it always did surprise me that PostgreSQL would be like, well, I got to scan these 40 million rows for you. Sorry, buddy. And I'd be like, wow, how did you even know there was 40 million rows without going and scanning all the rows and counting them?
if you've used Postgres, for instance, it has this thing called analyze that you can run on the table that will recompute the statistics and give you better, more accurate numbers on the number of rows and the number of
Hmm.
unique values. And
But what
also,
you're telling me is that the query planner uses those
yeah,
statistics. I
the,
didn't know that.
the query planner needs those statistics to do its cost based estimates. So, one of the problems with this approach is that if those statistics are wrong, all bets are off, kind of.
Yeah, yeah. I
Um,
mean, I think I always knew, of course, a query planner has to know which table's bigger or smaller, but I also had this dumb assumption like, well, it probably just uses whatever the start and end point on disk to figure out how big it is.
there's a paper that came out in 2015 that talks about it's got the fun title of "How Good Are Query Optimizers Really?" And one of the quotes in there is we have also shown that relational database systems produce large estimation errors that quickly grow as the number of joins increases, and that these errors are usually the reason for bad plans.
Hmm.
So even as of 2015, there were still issues around cardinality estimation. I read a paper literally from this year, I think in January, February, in CAACM about something called cardinality estimation graphs,
Hmm.
which is a research project trying to get better estimations on tables for the
Mm-hmm.
purpose of optimization. So
Mm-hmm.
this is still kind of an open problem.
Hmm.
But that said, these things, as we've mentioned several times, are still pretty much the standard. The optimizer that Selinger and her team built went into DB2, which was IBM's relational database offering. Postgres has a cost-based optimizer, although I read somewhere that Postgres uses this thing called the genetic query optimizer when the number of tables gets really large.
Huh.
There were a couple of follow-on frameworks that came out in the 90s, one called Volcano and then another one called Cascades, which were kind of cost-based optimizer frameworks. I believe the Volcano one evolved into Calcite. But yeah, just in general, the cost-based optimization using very much the same ideas that Solinger and her team put forth in 1979 are still largely in place in relational databases of our time.
That's amazing. Can you imagine you write a paper 40 years ago? It's going to be 50 years in a few years. And then that just becomes the way people do things in our field, which is just changing all the time, changing so rapidly. It's pretty cool, actually.
Yeah, I was surprised and a little disappointed that I had not heard of Patricia Selinger before looking for this.
Mm.
I guess part of the reason is because she didn't publish a lot after this. She became a fellow at IBM and she won the SIGMOD, the ACM SIGMOD award in, I think it was
2000s or something.
2002, I think. Yeah.
Hmm.
So, she's very prominent and you can find numerous interviews with her, but even by the standards of computer scientists, she doesn't seem to be very well known.
Hmm. Databases are the history database is interesting because these ideas have been just argued over and reworked and reworked, but the same kind of core ideas that emerged in the 70s are really still working effectively. That's pretty cool for a technical solution, software solution.
Yeah, I really enjoy this problem. I'm not sure we did it justice, but
Oh,
I
well,
would
it was all
people.
you. I just asked them questions. I'm not sure you did it justice, Mike.
I'm not sure I did it justice. Yeah, I should not blame you.
No,
But
I mean, I'm supposed to read the paper. I'm a co-host. I could not finish the paper. So I'm sorry, listeners. You should try to read this paper. I don't know. Maybe you find it readable. I could not get through it. The language, really, really, I just couldn't get through some of these sentences. I just couldn't understand what they were saying.
it's a little tricky, and when you get into the third and fourth joins, all of the potential options start to become a little daunting.
Mm,
They run through an example in the paper, and they have these trees. They have to calculate the cost for nested loop joins, and they have to calculate the cost for merge joins. And I guess one detail that we forgot to mention is that at this point in time, the only joins that they were considering are nested loop and merge joins. They wouldn't have hash joins until sometime in the 80s, I guess,
mm,
because they just took too much memory.
mm, mm. Interesting.
when you look at the interesting orders thing, so one thing I think I also forgot to mention is that the fields on which they join are also among the interesting orders. There may be cases where you have two possibilities of how to join on something,
Hmm.
but because one of them is part of the join criteria, it may work better to join on that index because you end up with a sorted result rather than joining on some other index and then sorting subsequently.
Oh,
Um,
interesting.
so those two paths may have to be considered.
Sounds like a pretty darn complicated problem to solve, and it's cool. Again, the solution is stuck for so long.
The approaches to it have changed a little bit. We talked about how they call this the left deep approach, and I guess over time people have done other versions of this dynamic programming problem, and one of them is what I one called bushy trees, which I kind of like. The idea there is that instead of sort of accumulating results from the left to the right, you can sort of split off A, B, C, and D. You can sort of join A, B, and join C, D, and then join the results together.
Oh, you could even
And
do this in parallel, right?
yeah, so that takes up considerably more memory. But the
Hmm.
benefit of it in modern computers is that you can do those intermediate steps in parallel, and then
Mm-hmm.
do the final join. So
Mm-hmm. Well, there's some cool stuff in there. I like the set theory stuff that emerges. That's pretty cool. It gives you a framework for thinking about it, that like an abstraction layer that allows me to understand it, kind of what's going on, I think. Um, Thanks for making me read this paper, at least making me read the first few pages a number of times. And this has been Picture Me Coding with Eric Aker and Mike Mull. Thanks so much for hanging out with us. We will see you again in a couple weeks.
see you next time.